All right, we're going to continue with section 15.3 in this video. We're going to look at another example. So example, let the vector field f of xy be equal to negative y over x squared plus y squared, and then x over x squared plus y squared. Compute the curl of f and the line integral over c of f dot dr, where c is the circle x squared plus y squared equals 1. All right, so first let's look at the curl of f. So one thing, remember now, since we have a vector field in 2 dimensions, this is our m and this is our n, so the curl of f is just equal to the partial of n with respect to x minus the partial of m with respect to y. So the partial of n with respect to x, we're going to get 1 times x squared plus y squared, and then minus x times 2x. Oh, sorry, this should have a k on it. That's the curl. X times 2x, and then all over x squared plus y squared, quantity squared. That is our partial of n with respect to x, and then minus the partial of m with respect to y. We're going to get negative 1 times x squared plus y squared, so we're going to get negative x squared minus y squared, and then minus, what am I doing? Negative y times 2y. All over x squared plus y squared, quantity squared. So times k. So we have a common denominator here, so we can combine terms. So we end up with x squared plus y squared minus 2x squared, and then plus x squared right here. So we have an x squared plus an x squared. So that's 2x squared minus 2x squared. So that, and that cancel. So we end up with y squared here, and then plus y squared, which gives us 2y squared. And then here we have another 2y squared, but that one is negative. So is that right? Y squared plus y squared and minus a 2y squared. So we do get 0. So this cancels with that and that. So we do get 0. 0k, or the 0 vector. Alright, so we have our curl of f. Now what we want to look at is we want to compute the line integral over c of f dot dr. So the line integral over c of f dot dr, and I'm going to parameterize c. C was x squared plus y squared equals 1. So The parameterization for that is x equals cosine t, y equals sine t. So if you're asking yourself, or hopefully you are asking yourself now, why am I parameterizing c? Why not use the fundamental theorem of line integrals? And we'll talk about that as we go a little bit further in the problem. All right, so this was from t goes from 0 to 2 pi. All right, so now how we compute this, remember, we compute that's the integral from 0 to 2 pi of f of r of t dotted with r prime of t dt, where our r of t for us is cosine t comma sine t. So now our r prime of t, we'll go ahead and find that now. R prime of t equals negative sine t comma cosine t. So now if we put everything into here, the integral from 0 to 2 pi of f of r of t. So we're taking this and we're putting it in for all of our x's in the original vector field we were given. We're taking sine 2, putting it in for all of our y's. So in that vector field that we were given, the denominators were x squared plus y squared in both terms. So we'll just get 1 in our denominator for both of them. And then our numerators were negative y and x. So we're going to get the vector negative sine of t. So negative y over 1. So because it's over x squared plus y squared, which is 1. And then x cosine t over x squared plus y squared, which is 1. So this is f of r of t. Oops, I'm missing a parentheses. This is f of r of t dotted with r prime of t. So negative sine of t. And then cosine of t. And we'll integrate that with respect to t. And we take this dot product, we get sine squared t plus cosine squared t. So we just get 1 as our integrand. So we're integrating integrating from 0 to 2 pi, 1 with respect to t. So we would just get this equals 2 pi, which, now let's discuss a couple of things here. So, which is not equal to 0. So what we did is, first off, we looked at the curl of our vector field f, and we got the 0 vector. And what we've been doing every time we do that is we say, okay, well, the curl of f is equal to 0, the 0 vector. So we find a potential function f, and we can use that potential function for whatever. In this instance, we could use that potential function if we wanted to find the line integral over some curve c, not necessarily the c that we're talking about, of f dot dr. We would just need the endpoints of whatever the curve c is. Now our curve c is closed, so the start and end points would be the same thing. So the start and end points being the same thing would say that we would do, if it were independent path, we would have f of the start point minus f of the end point, where f is a scalar function, and that will give us 0. So if we go back to the 4 equivalent statements we had that f is conservative, and this is all under certain conditions. F is conservative, the line integral over some curve c of f dot dr is independent of path. The line integral over some closed curve c of f dot dr is equal to 0, and the curl of f is equal to 0. The 0 vector, all 4 of those are equivalent, but that was under the proper conditions. So notice here, we got the curl of f was equal to 0, but we took a line integral over some closed curve c and got something that was not 0. So there's something in those 4 equivalents we're seeing something that's falling apart in there. Now, why is something falling apart in there? It's because the conditions for all four of those things to be equivalent say that your vector field has to be defined everywhere. And notice our vector field is not defined at the origin. So all the things that we've been doing in other problems will fall apart entirely if we don't pay close attention to where our vector field is defined. Because it's not defined at the origin, we see that this vector field is not independent of path, but those equivalences don't hold. So you can't say because it's not defined at the origin that none of those things in there hold, but it's just some of the things in the equivalence may or may not hold now because the conditions under which we can use that equivalence, which are these conditions, actually are not met now. So we really shouldn't be talking about those four things in conjunction with one another at all in an example like this. So what I'm trying to get is just make sure you pay close attention to the domain of your vector field before you go into trying to use the curl of f is equal to 0 and assuming that you have a potential function or that you're independent of path or that over a closed curve that you'll get 0 if you evaluate the line integral. Alright, so I'm going to stop this video here and then we'll continue with section 15.3 in our next video.